So let's come to network meta-analysis. The aim of this talk is that you should understand the background for network meta-analysis, the principal model and the underlying assumptions, how to assess the heterogeneity and the special heterogeneity which arises in network meta-analysis, the inconsistency, and how to assess the evidence flow in network meta-analysis. So the objectives are that you are able to carry out a network meta-analysis to report and visualize results and interpret the results taking diagnostic measures and graphics into account. Okay, as we have heard already, classical meta-analysis play an important role in evidence-based medicine since they are allowed to summarize the treatment effects of clinical trials that compared the same two treatments. In the case if more than two treatments should be compared, this can be done by a network meta-analysis since this connects the evidence of different studies. So network meta-analysis is also called multiple treatments comparison or mixed treatment comparison. And it allows to the comparison between a set of treatments. Its motivation, the British National Institute for Health and Care Excellence that published guidelines to the use of established and new, for example, established and new pharmaceutics, published a guide to the methods of technology appraisal for decision-making methods, and they have a preference for data from head-to-head randomized clinical trials. But when there is evidence from mixed treatment analysis, and if this add information, we can also consider this into the analysis. And if data from head-to-head randomized clinical trials are not available, we can use indirect treatment comparisons as well, which the indirect treatment comparison, which is a part of network meta-analysis. Here is an example of a network meta-analysis, which is published by Sen et al. In 2013, and they compared 10 treatments, 9 glucose-lowering agents and placebo, regarding a continuous outcome, the change in glucose concentration in patients with type 2 diabetes and a baseline therapy. In this network meta-analysis, 26 randomized clinical trials could be included, 25 two-arm studies and 1 three-arm study, and so we have in total 28 pairwise comparisons of these studies. In the context of network meta-analysis, the design of a study is often defined by the set of treatments compared within the study, so that the design of a two-arm study and a three-arm study that partially compared same treatments have different designs. So here an example, studies that compared placebo to one treatment, AK, has a different design to studies that compared the 3 treatments, placebo, AK, and MEDF. The corresponding evidence network to this network meta-analysis is shown on the right side. The 10 treatments are arranged circularly, and treatments that are compared in at least one study are connected by a line. And the thickness of the line is proportional of the amount of evidence for this corresponding treatment comparison. So the thicker a line, the thicker the amount of the thicker a line, the greater the amount of evidence, which means in this context that the evidence is measured by the inverse standard error of the aggregated treatment effect, aggregated over all studies that compared the respective 2 treatments. So in this evidence network, we have 15 out of 45 possible edges. So there are treatments that are not compared directly in one study. But the question that arises now is which of these treatments is the most effective? And this question can be answered by doing a network meta-analysis, and this is only feasible since also indirect treatment comparisons are included in this analysis. What does an indirect treatment comparison mean? in this example, we have, for example, 6 treatments here, shown in this forest plot, that compared treatment Rossi versus placebo. We can aggregate the treatment effects of these studies and obtain a mean difference in this case of minus 1.15. And we have, in addition, studies that compared metformin versus placebo. So we can aggregate the treatment effects per design here, and by subtracting this aggregated treatment effects, we can indirectly infer to the treatment comparison between METF and Rossi. And we also obtain the variance of this indirect effect estimate when we sum up the corresponding variances of these direct effect estimates. If we have, in addition, direct evidence for this treatment comparison, METF and Rossi, here the example, we have 2 studies that compared these 2 treatments directly. We can combine this evidence. We can combine the evidence of the indirect evidence, or the indirect comparison, and the direct comparison. So therefore, we can use the inverse variance weighting method we have seen before in classical meta-analysis. So the estimate of the direct estimate and the indirect estimate can be aggregated, and also the variance of the network estimate can be calculated. Okay, the underlying assumption for this, that we can do indirect treatment comparison and network meta-analysis, is the transitivity. The transitivity that an indirect comparison validly estimates an unobserved head-to-head comparison. This transitivity cannot be tested statistically, but can be evaluated conceptually or contextually. But in contrast, we can assess the so-called consistency, which is extension of the transitivity, that the direct and the indirect estimates are in agreement. So this can be tested if we compare the direct and the network estimates, taking the corresponding variances into account. So in network meta-analysis, a further aspect of heterogeneity arises. In addition to the heterogeneity between studies within designs, there might be heterogeneity between designs, which is called the consistency, or the inconsistency in this case. Okay, for estimating network estimates, so we want to estimate all pairwise treatment comparison in network meta-analysis. There exist different models and estimation methods. There are Bayesian approaches, and therefore we can use the software Winbugs or the R package GEMTC. There are frequentist approaches, for example, using two-way linear mixed models with main effects treatment and trial, which where we can find further information in the publication of PIFO, and he used the software SAS to implement these methods. We can also, we have heard that network meta-analysis is a special case of multivariate meta-analysis, multivariate meta-regression, so we can also use the R package MVMeta to conduct a network meta-analysis. And there are 2 further approaches, 2 frequentist approaches using generalized least squares to estimate the network estimates. These 2 approaches use or takes the correlation of comparison of multi-arm studies in a different way into account. So for multi-arm studies, the treatment comparisons are correlated. We want to take this into account when we analyze or when we estimate the treatment effects. And the first approach reduces the dimension. So each study with P treatments gives P-1 comparison to a reference treatment into the analysis with the corresponding standard errors. And the second approach is an approach of reducing weights, where all pairwise comparison of these multi-arm studies are analyzed and go into this model. So we use all pairwise comparisons between the treatments of multi-arm studies, but adjust the corresponding standard errors. So it's shown that both approaches lead to identical estimates. So these two approaches are implemented in the R package NetMeta, which I will present now in further detail. So first I will present the fixed effect model using the method or the approach of reducing dimensions. This is shown here with y, the vector of observed treatment effects. So each two-arm study gives one entry, and each multi-arm study gives with p treatments gives p minus 1 entries to this vector of observed treatment effects. And each study gives also the variance to the covariance matrix. So the covariance matrix of this model has diagonal form. For each two-arm study, we have one variance on the diagonal, and for each multi-arm study, we then block on this diagonal, taking the correlations between the treatment comparison of multi-arm studies into account. X is the matrix, the design matrix that contains the structure of this network. And theta NMA is the vector of parameters we want to estimate in this analysis. So for network meta-analysis, we choose one of these treatments as a reference treatment and estimate by this model all treatment comparison to this reference treatment. And all other network estimates can then be calculated by linear combinations of these basic contrasts. So here an example, we have a network with 3 treatments and 4 independent studies. Two studies with design AB, 1 study with design AC, and 1 study with design BC. So for these 4 designs, for these 4 studies, or two-arm studies, we have 4 entries in the vector of observed treatment effects. And we have the corresponding covariance matrix with the 4 variances of these studies on the diagonal. And the design matrix contains one column for each treatment that is compared to the reference treatment in the network. So we choose in this example treatment A as the reference, and then we want to estimate the treatment effects A, B, and AC. So we have one column here in this design matrix for treatment B and one column for treatment C, and one in the corresponding column of the treatment that is compared to the reference treatment in the network, or if the reference treatment in the network is not included in the study, we have there a -1. So this design matrix is based on the assumption of consistency in this network. We can fit this model alternatively in 2 stages. The first stage is to aggregate per study, to aggregate the studies per design by multivariate meta-analysis. We have seen this in the session before. The aggregation step, the inverse variance weighting method for in the multivariate sense. So if we have in our network studies that compared more than 2 treatments, if we have multi-arm studies, we can use this formula to aggregate the treatment effects and the variances per design. In the case of the 2-arm studies, these are univariate formulas. After aggregation of the direct effect estimates and the corresponding variances, we can use them to fit the model in the second stage. So back to the example, with the 4 studies, we aggregate the treatment effects of the AB studies and have 3 entries in the vector of observed aggregated treatment effects. We have only 3 rows, and we estimate the same vector of parameters in this case. if there is a further study of design ABC, this contributes 2 new parameters that have to be estimated, and a covariance matrix, which we can find then in the covariance matrix on the diagonal. Okay, this is the model, and for estimating these treatment effects, we can use the R package netmeta. Therefore, we have to install the package and to load the package, and then we can have a look on the implemented data, for example, the send data, which I have introduced before. So here we have a part of this data set. We have the mean difference per study, the corresponding standard error, the treatments that are compared in this study, and one column with the study label. And for the package netmeta, it is important to have in the data all possible pairwise comparisons of all studies. So we have here one 3-arm study, and therefore we have to given data set where 3 rows are where we have 3 rows for the 3-arm study, corresponding all possible pairwise comparison in the 3-arm study. Okay, for conducting the network meta-analysis, we can use then the function netmeta. So by this function, we generate an object of class netmeta, and like in the package meta, we can use the functions print and summary for this object, and the function forest as well. And there are further functions. We have the function netgraph, netheat, decomp design, and netmeasures as well. We have to give there the treatment effects, the standard error of the treatment effects, and the compared treatments. These are mandatory arguments. And the 5th argument, the study label, is important since by this argument the multi-arm studies are identified. And similar to meta, we give the data and the summary measure. And here we can also choose one treatment as the reference treatment. If the comparison to a reference treatment is of primary interest, we can specify this reference treatment here. The data has not to be sorted before using this function. This will be done by the function. And yeah, then there will be such a warning that the treatments within a comparison have been resorted in increasing order. Okay, we've generated an object of class netmeta, and now we can use the function netgraph to produce this netgraph. We can choose here, for example, a sequence for the arrangement of the treatments anti-clockwise. Or we can give colors for the edges, or we can specify if we want the thickness proportional to the inverse standard errors or not. Okay, and if we now print this object NMA, where we specified that we only want to have 2 digits. Firstly, we see in the output the original data. We have also 1 row for each comparison of each study. So we have also here 3 rows for the 3-arm study. We have here the original data, the treatments that are compared in the study, the treatment effects, and the standard error of the treatment effect. And then we have here, in addition, a column for the adjusted standard error of the treatment effect. So these 2 columns are the same for 2-arm studies, and for 3-arm studies, they differ. here, and here. And we have a column that contains the number of treatments that are compared in the respective study. And if there are multi-arm studies, these are marked by a star in the last column. Further in the output, we obtain the number of treatments in each study. The studies are alphabetically sorted, and we obtain here a column with a number of treatments in this study. So also here we can see the study Wilms 1999, who compared 3 treatments. And next, we obtain the results for the network meta-analysis. So we have here a column with the mean differences estimated based on the whole network and the corresponding confidence intervals. The next column contains the contribution of each study comparison to the Q statistic of the whole network for assessing the heterogeneity. And the last column shows the leverage of each study. We know the leverage from classical linear models, and similar here. Small leverage means that the precision of a contrast benefits largely from the indirect inferences in the network, and if we have a leverage of 1, this means that there is no gain at all from the remaining network. So we can see the comparisons of the 3-arm studies gain a lot from the remaining network, especially from studies that compared the respective 2 treatments here. In the output, we get also the number of studies that are compared, the number of treatments, the number of studies that are involved in the network meta-analysis, the number of treatments that are compared in the network meta-analysis, and the total number of pairwise comparisons. And since we have specified a reference group, we obtain all the estimated treatment effects to this reference treatment placebo here. If we don't specify a reference group, we obtain a matrix of all pairwise treatment estimates in this network and a matrix of the lower as well as a matrix of the upper confidence limits for these estimations. We can use also a random effect model for network meta-analysis. So we have a further vector here of random effects, and we have a further component in the covariance matrix, the covariance matrix of the random effects. Therefore, we have to estimate the tau square like in classical meta-analysis, and we can use therefore also a generalized Simonian-Laird method. And for this, we have to do some assumptions. One assumption is that this tau square is the same for all designs in the comparison. Otherwise, there would be a great number of tau squares that have to be estimated. And a further assumption we take here is that the random effects of multi-arm studies have correlation 1/2. So back to the example, the simple example of 4 studies. 4 studies of these designs, and then the covariance matrix. This first covariance matrix is the same as we have seen before. We have here a block on this diagonal for the multi-arm study, and in addition we have here the covariance matrix of the random effects, which contains here the assumption of the correlation of random effects of 1/2. How can we conduct this by the net meta function? We have to specify here the argument random equal to true. But even though if object net meta has been generated without this argument, the information in the random effect network meta-analysis is only part of the object net meta. But we can use this for the next function. I will show the forest function. A further part of the output is the estimated tau square in the random effect model, as well the calculated I square. So we can see here a large amount of heterogeneity, and we have also here a test of heterogeneity and inconsistency of the whole network with a p-value smaller than 0.0001. So we can see here a large amount of heterogeneity in this example. With function first, we can now plot a function first of the treatment effects. This first plot is a little bit different from the first plot we know from classical meta-analysis, since we expect for different treatment comparison different treatment effect estimates. And we have shown here the treatment comparison of all the treatments to one reference treatment, in this case placebo. So we cannot assess here the heterogeneity between, but we can visualize the estimated treatment effects compared to placebo. And we can do this also for the random effect model, and we can see that due to the large amount of heterogeneity with larger confidence intervals of the estimates, so that the last three estimates are not significant on the 5% level. But when we compare the treatment effect estimates, they are very similar in this case. Okay, we have seen there is a large amount of heterogeneity. We can assess this in further detail. So we have, like in the multivariate meta-analysis, a Q statistic generalized for multivariate meta-analysis, since we want also analyze the multi-arm studies. So, and we have here the squared Pearson residuals, the residuals between the observed treatment effects on study label to the effects based on the network. And this Q statistic is chi-square distributed with degrees of freedom equal to the sum over all studies, the sum of the number of arms in this study minus 1 minus n minus 1, where n is the number of treatments, and a is the number of arms in study S. In the first version of the slides, there was a minor typo here. So note, if you have here S as a subscript S, this should be a subscript S on your slide, on the slide. Okay, this Q statistic for the heterogeneity in the whole network can be decomposed, so that we have a Q statistic for the heterogeneity within designs or within pairwise comparison, alternatively, and that we have a Q statistic for the heterogeneity, also called the inconsistency between pairwise comparison or between designs. We can obtain these Q statistics by the netmeta package. If we use this $ and Q, we obtain the Q statistic for the whole network, Q point heterogeneity, the Q statistic for the heterogeneity within pairwise comparison, and by point inconsistency, the Q statistic for heterogeneity between pairwise comparison, and also a decomposition of the Q statistic for the heterogeneity within comparisons, decomposed for each comparison. And alternatively, if we want to decompose the Q statistic in the whole network, in design components, we can use this function decomp design, so that we obtain a Q statistic for the heterogeneity of the whole network, heterogeneity within and between designs. These are very similar to the Q statistics before, where we decompose the Q statistic respective the pairwise comparison. What we can see in this example is that that what we have seen before, there's a large amount of heterogeneity, and we can see we have heterogeneity within designs as well as between designs. And the heterogeneity within designs can be further decomposed for each design. We can see there are a lot of designs that have only 0 degrees of freedom. So this is because there's only one study that compared, for example, these two treatments, and therefore there are no degrees of freedom to assess the heterogeneity for this design. And we had 5 designs with more than one study, and 4 of these 5 designs show also heterogeneity between the studies within this design. Okay, there is a possible plot in this NetMeta package for locating inconsistency in further detail. So we have seen there's inconsistency, and when we want to know where in this network is this inconsistency, we can use this net heat plot, which can be called by the function net heat, and I will explain this plot in further detail in the following. We have this Q statistic for the heterogeneity between designs, for the inconsistency, which is a sum over all designs of the squared Pearson residuals between the direct effect estimates and the network estimates. With these degrees of freedom, namely the sum over all designs of the number of treatments in each design -1 minus the number of treatments in the network -1. So in our example, we obtain this Q statistic of 22.5 with 7 degrees of freedom. So we have 14 designs of 2-arm studies and 1 design of 3-arm studies. So 16 minus the number of treatments are, in the example, 10 minus 1 is equal to 9. So we have 7 degrees of freedom in this case. For locating now the inconsistency in the network in further detail, we use an algorithm. We fit a model that allows for a deviating effect in one design D. So we extend the model with further parameters for each comparison in this design D. So we relax the assumption of consistency for one design D. Then we recalculate the Q statistic after this detaching and assess then the changes in each summand of this Q statistic after this detaching. We use this algorithm for each design in the network and visualize these in this plot by the colors. So an increase is visualized by warm colors, which means there is inconsistent evidence. And if there is a decrease, we visualize this by cold colors, which mean there is supporting evidence of design D, which we detach for design D prime. When we go back to the example, we have this Q statistic of 22.5. Then we detach, for example, design met fuel and can recalculate the Q statistic. Now we subtract all the summands and obtain this vector, which we visualize on this scale. And obtain, after detaching of the design in the column, this color column. On the diagonal, we have the contribution of the design met fuel to the inconsistency statistic. And we can see that after detaching of the design met fuel, we can see here that the contribution of these designs to the inconsistency statistic increases, though it's a sign for inconsistency. And we can see that here the detaching of this design decreases the contribution of design A casual, which is a sign for supporting evidence. So we can detach one design after each other in the network, obtain this matrix of colors, and we order the columns and the rows in the same manner using a clustering algorithm and obtain this color matrix. Since one deviating effect in a network might have side effects on the network estimates of other designs, we also want to visualize the evidence flow in this network, also in this plot. Therefore, we have a look on the edge matrix, which projects the direct effect estimates to the network estimates. So we know from, which we know from classical meta-analysis, but here also the non-diagonal elements are important, since each network estimate, for example here METFSUAL, is a linear combination of all direct effect estimates here in the column. So the network estimate for this design is 56 times the direct effect estimate of this design, plus 28 of the direct effect estimate of this design, and so on. And we use now these coefficients of the linear combination to visualize the contribution of each of the direct effect estimates to the network estimate by the area of gray squares. And the greater the area of a square, the greater the contribution of the direct effect estimate in the column to a network estimate in the row. So we obtain for all the network estimates in the rows this matrix, and we combine this with the colors. What can we see here in this plot? We can see there are designs here, for example, without color, but gray squares, which means these two designs have a great impact on each other, but in a consistent way. There is no color. When we have a look on the colors on the diagonal, we can see the contribution of each design to the inconsistency statistic, and we can see that the first 4 designs have the greatest contribution to the inconsistency statistic. The network estimate, for example, here, Black-Rossi, is mostly driven by its own direct effect estimates, since this area of the gray square is very big. And due to the clustering algorithm we have used for the color, we can see that there is a hotspot of inconsistency between the first 5 designs. So we can limit the inconsistency in the network to these 5 designs, and then, like in classical meta-analysis, we want to assess which are the sources for this inconsistency, and we can use subject matter considerations for subgroup analysis or meta-regression to analyze why are there these inconsistencies. Okay. Do we have enough time, or? Yeah. Yeah, okay. So like in classical meta-analysis, it is important for an estimate to know how this estimate depends only on single observations. And in network meta-analysis, it's interesting how depends a network estimate on direct evidence. So we can calculate in network meta-analysis and measure for the direct evidence proportion. It is also interesting which is the mean path length for network estimates. So short mean path lengths are nice, since there is not so much uncertainty for this network estimate. And it would be nice for one network estimate to have other network paths that calculate the same estimate. So it's interesting for a network estimate how much is the parallelism of network path for this estimation. So in Koenig et al., we find these 3 definitions of measures for characterizing the flow of evidence. to explain this on two simple examples. The direct evidence proportion, we have the network of 3 treatments, and we have a look on the network estimate of the comparison between treatment 1 and 2. The direct evidence for this is 2/3, and 1/3 is estimated by the indirect evidence. And the mean path length, 2/3, we have one component of the path, and 1/3 are two edges for this path. So in mean, there are 430 of mean path length. And for the minimal parallelism, we can see that half of the direct evidence is paralleled by indirect evidence, so that we have a minimal parallelism of 3.5. This example here on the bottom, we have more edges and create a network. We want to estimate the treatment effect between treatment 1 and treatment 2. We can see there is no direct path. The direct evidence proportion is 0. And the mean path length for all these paths from treatment 1 to treatment 2 is 4. And we can see the minimal parallelism here. The minimal parallelism is 2 in this example. These measures can be calculated also by the net meta package using function net measures. We can obtain the direct evidence proportion, so we can see, for example, here that these edges where only one treatment is connected in the network have a direct evidence proportion of 1, and they have not gain of the remaining network. And we can calculate mean path length and minimal parallelism, and we can see the minimal parallelism here is 2.3, so there is no much connectivity in this network, but also only indirect and mean path length of 3.1. Okay, we have seen that by network meta-analysis, the estimating of the effects of all pairwise treatment comparison in a trial network is possible. This is feasible since indirect treatment comparisons are taken into account, and therefore we have the assumption of the consistency in this network, which we have to analyze in addition. But issues known from classical meta-analysis arise also in this case. We want to analyze the heterogeneity, and here the further aspect of heterogeneity, the consistency in the network. There might be limited power for assessing heterogeneity if we have small number of paths in this network. There might be selection bias, and it's interesting to which extent results rest on a few studies. So our package, NetMeta, provides the methods for estimating treatment effects, but also further methods for diagnostic are implemented, the decomposition of the generalized Q statistic, the net heat plot for locating inconsistencies and possible drivers for these inconsistencies, and measures for characterizing the evidence flow. Okay. Are there any questions? Okay. So we can examine this. Yeah.
Yeah, there is a question.
Yeah, one question.
How would you interpret the result of the network looking at the forest plot simply, or
when you have a look at the first plot, you can see the estimated treatment effects.
yeah,
But then you have also to take into account, is there heterogeneity, like in classical meta-analysis?
okay, and in addition the possible inconsistencies.
Yes.
And if it is too large, what to do, how to interpret.
Then it would be nice to find sources for this heterogeneity, like in classical meta-analysis, to do meta-regression or something like this.
So you still use the classical methods to
Yes.
interpret the results, let's say, and to support the interpretation of the results.
Yes.
So you can estimate then a comparison of two treatments that, well, indirectly, right? My question is, when is it more useful to have that? For example, if somebody's gonna design and study comparing two treatments that they have not been compared before, are people using this methodology to get a first idea of the parameters for the design?
Yeah, it's possible. If there are no direct evidence for a treatment comparison, we can use studies of other designs with other treatments to infer indirectly to this treatment comparison.
Is there another way of looking at publication bias within this system?
You can assess the publication bias for single edges, so for single designs. But
there is
there's
literature
a
coming
new-
for publication bias. This is especially papers by Dimitris Mavridis from Ioannina in Greece, who works about this. And he has written, I think, yes, there's one paper already published, and another paper is soon to be published. So I know this because I was the peer reviewer. And there's also another model cited there. I've forgotten the name of the author. So there are first approaches, and what Mavridis does is the a generalization of the COPAS model for network meta-analysis. So this is coming now because all these new stuff like publication bias and network meta-analysis to get together all the problems. So it's quite recent literature there. So it's not implemented in our package, for instance. So we have also no meta-regression in this package here. You can do meta-regression with network meta-analysis too, but then you have to use either the Winbugs code, so another software, or the MV meta, because it's very general, or meta 4. These are already there.
So what you can do in this two-stage analysis is in each individual analysis, you can do an adjustment for publication bias, say regression, and then you can bring that together into the second stage. But in the package that you've been talking about, because it does both those stages in the actual one step, you can't actually do it with this package, but that would be how you would do it. So the papers that Goethe refers to actually do the whole thing in one step, don't they? So they have a joint model which I think does the publication bias
So
and the thing.
there's a joint model in the of COPAS model type for all together. So it's very complex, of course. So it's very advanced.
My take on it is that it's a very heroic analysis to try and do all that in one take. So, yeah.
But in general, to network meta-analysis, one has to have in mind that the question leading to network meta-analysis is very, very natural, because this is the physician who has a patient with a certain condition, and there are 20 treatments on the market for this condition. And the question is very, very natural to ask which treatment of all these treatments is the best for this patient. So looking at the literature, at all the literature for all treatments of this condition naturally leads to a network of treatments and a network of existing studies. And if you look at all this existing evidence, then you have automatically the question of network meta-analysis. That doesn't mean that the solution is easy, but the question is very, very natural. So it is a very advanced method, but it is very, it's also very necessary to have methods for this. And clinicians ask for this, so it's very well known, and there's a sort of a hype in the medical field about network meta-analysis now.
So, is there any other questions? So, what we've got now is we've got this bias practical, we've got the MV meta practical, and we've got a practical on network meta-analysis. So, what we would suggest is that you sort of work through these, and there's a chance to use some of these data and create some of these graphs and try and interpret them, and then we've got the interpretation also described in the solution, and you can cross-check that. And so this concludes, I think, the sort of formal part of the presentations for today. So we'd like to thank you very much while we're all together for coming to the course, and as I say, we'll be around to help with the practicals for the next period. Okay, thank you.